So let's today talk about something which is intriguing and is also the core of quantum mechanics, as because it's not some a topic, it's actually equation of quantum mechanics, which is known as uh, Schrödinger's equation. Okay, in short, SE. So what Schrödinger equation actually is, if I write Schrödinger equation, O has two dots on the top. So in Schrödinger equation, when we talk about what it is, it's a mathematical way and a very important part of quantum mechanics to explain what happens in quantum mechanics in form of mathematics. And even solving the equation gives us solutions. And when I say solutions, I mean probabilities. And if I write what Schrödinger equation actually is, it's E is equals to H bar. Sorry, not wait. H bar, and both sides are multiplied with psi. Okay, they multiply with psi. Oh, sorry, wait. Uh, Multiply with psi, and this psi actually can be written as psi is equals to psi of x times not omega t. Or we can just remove this and we can just write it like normal. So this is here. What's the difference between this psi and this, and what's the difference between this psi and these two? So this psi is, it has both the position and time property of the particle or the system, but when we talk about its what it is product of, we say we then they're separate. This is position as separate and time as separate. Now later on we will talk about why this equation is also an important part of what we will be talking about. So when we like try to drive this equation, uh, there are two. Wait, sorry, not this E. This is H actually. This is H. Now, when we derive the equation, actually, whenever we have something, a quantity, and it is multiplied with psi, a function, this wave function, it becomes a operator. Okay, it becomes an operator. So that's why I have to put a knot at the top, a hat. It's called a hat. It does look like a hat. So then, uh, when we say what is h is equals to 1 by 2 mv square plus v. Now, what is 1 by 2 mv square and v? 1 by 2 mv square, of course, from the as the classical physics, one of the main things is kinetic energy. Okay, energy because which is gained because of movement, and then we have potential energy. Okay, in Schrödinger equation, most of the time, only either E is changed in the final form and as a kinetic energy is changed, but this potential energy is kept the same. You will notice in the final form. So when we talk about now for our for our like for step-by-step formula derivation, we actually need to change this kinetic energy into another form. And how we do is I can write 1 by 2 mv squared as 1 mv squared over 2, right? And if I multiply these this equation by m and divide it by m, so what will happen is that this m will become m square, or the upper one, and v square remains the same over 2m. Now I can write this m square v square as mv square. Okay. Now when I write mv square whole square, we all know that what is mv. Mv is nothing but a momentum. What it is? Momentum. So then this mv can be replaced as p is p square over 2m. So then if I rewrite this equation, actually the name of this h is, let me write the name of the h. It has a special name, Hamiltonian, named after the guy who came up with it. Hamiltonian. Okay. Then Hamiltonian. Okay, Hamiltonian. Or and when you have a hatch, you get a Hamiltonian operator. Now, rewriting the equation, I get h is equals to p square over 2m plus v. Now, you remember I multiplied h with psi. So, if I rewrite it as multiplied by psi, then I get this form plus v of x. It's actually v of x psi. Okay. Then what happens is, okay, and one more thing. Whenever we write some quantity and then we write psi with it, so if it's on the left side or the right side, then if psi is on the right side, it means it's acting on that let's say what quantity, okay, which results results in a observable. Okay. Now we won't talk in detail about this because that's not our main topic today. Our main topic is a derivation of Schrödinger equation, and also then we will talk about why this part is also important. So now we have derived, we have expanded h into 1 by 2mv squared, then into p square over 2m plus v. Now rewriting the whole thing again, e of psi is equals to, now instead of h I'll write p square over 2m plus v of x and multiply by psi. Okay. Now what is p? We can rewrite p as well. P is equals to h over lambda in when we talk about quantum mechanics, where h is known as famous Planck's constant. Okay, it's known as Planck's constant. It's a very interesting value. It's a very short value. In term powers of 30, it's negative to the power negative 34. So then to the power negative 34. Then when we talk about, okay, now we have this equation p is equals to h over lambda, and then we have another equation known as k is equals to 2 pi over lambda. Now when we combine these two equations, okay, we get a new equation known as P is equal to H over lambda, and then we know that when we replace lambda into the equation, we get 1 over 2 pi over k. Just rewriting this as lambda is equal to 2 pi over k. So we get, what do we get? We get reciprocal it will become h multiplied by, not lambda, it's k actually, k, and this becomes k over 2 pi. Now we do, and then one important thing here, this part of the equation, this is actually a k, this is a k, sorry for writing it. H over 2 pi is actually known as h bar. This is Planck's constant, and this is same thing but reduced, Planck's constant. Okay, and this is even a smaller value. Then rewriting it, we get h bar t, sorry k, not t, k, what is it, k t. So then we just changed p is equals to h over lambda to p is equals to h bar k. Now this is also another important equation in our steps in our path to deriving Schrödinger's equation. So right now what we're doing is we are accumulating the data we need to combine and make the Schrödinger equation. Without them, we won't be able to do it. Now, I have this equation, P is equals to H bar K. I have this equation. And then another one. Another very important part of our equation is E. Now, E also has a form. We know that E, what's happening? E is equals to H, HF, right? And you know what this is? It's actually energy of a photon, right? Energy of a photon. So, and here, this guy we have, which is known as frequency. I can write it as 2 pi over omega. Where omega came from? From the equation omega is equal to 2 pi f. When you make f the subject, you get omega. This omega. It's actually we don't need to get into depth of what's omega actually. So when we do this, we get f is equals to 2 pi over omega. Is it 210? I think so. So it's 2 pi over omega, and then replacing it, we get h is equals to h. Wait, did I mess up somewhere? Oh, sorry. It's actually not 2 pi over omega. It's f is equals to omega over 2 pi. Okay. Now multiplied by omega over 2 pi. Again, we have something similar to h over 2 pi, which becomes h bar omega. Okay, this is another equation we require. Now, we have derived every part we require for the Schrödinger equation, which we will be using in this form, from this form. Now, to do this, what we do is we will do derivation. Okay, now what we will be derivating, I already said, in many times I wrote psi. I wrote again and again. I wrote psi, but I never wrote what psi is. Right? I never wrote what psi is. And then you would say, what psi is actually this, right? This split form, but it's not what psi is. It's the what psi has in its as a something it stores the position and time of that system. But as what psi is, it's a function. As its psi is, another name is wave function, and psi can actually be written as a e to the power I kx minus omega t. You don't need to know how this equation comes up in the derivation, as it's not required for now. So when we talk about this, okay, now here, if I rewrite this equation over here as what I got e of e psi x by t is equals to x or with this of x and t, psi with x and t, and then we have p squared over 2m psi x and t. Remember, whenever you multiply, whenever you multiply psi, this becomes a operator, plus v of x operator, we get psi. So I multiplied what psi inside in this on the right side. Okay, now I'll expand. Now I'll expand it even more, as we know that p and e also has forms. It becomes h bar omega psi is equals to p is I k square over 2m. Right. P is not wait. Sorry. I'm getting too ahead of myself. It's h bar. I will be there, but not right now. H bar k. Why can't I stick with one color? Plus v of x psi. Now, this is not a final form. We still need to bring in space and time, because we don't have the right side has time, or not as what I'm saying, but the final form requires the derivations, okay, and it's not the final form. So what we can do is, we remember this equation over here at the top, we derivate it, okay. What we do is that we derivate it. For the right side, it's a position dependent, and the left side is a time dependent. Okay, so we can write it as, so one more thing, sorry, I forgot. If I write it as this becomes a not I. If I don't expand this, I'll tell you what I did. D psi by dt is with respect to, not with respect to time first, we'll do with respect to position. You'll know what I'm doing. D psi by dt or dx is, we know that equate the derivation of e to the power x is e to the power x. So what we do is that it may simply to put is, it's actually, and the derivation of the power multiplied by e to the power, the same function again. So it becomes, if we multiply with respect to x and I multiplies in, we get I k, and as we're just multiplying with respect to x, we don't write x decreases to 1. So it becomes e I kx minus wt. Then we do second derivation because it's a second order derivative on the right side. So we get ik squared, as you're doing the same thing and you're taking it, multiplying with the same quantities, and you get I variables, not quantities. And this is another form. So this is a second order derivation, second order. So we get, what is it? It's d square d psi by d square d square psi by dx square. Now wait a minute, doesn't this seem very similar to what we have over here, right? Doesn't seem similar? If I take and this over here, it's the same as the original one, what we have over here. So I can write d square by d square psi by dx square to write ik square d psi or psi. Then if I multiply square in, I get I square k square psi. Now what is I square? We know that I is equal to square root of -1. So what does I squared turn into? Square root cancel. So square root cancel, we get -1. So what this equation becomes, d square psi over dx square is equals to -k square psi. Now this becomes d square psi over dx square is equals to psi, not psi, k square psi, but this side becomes negative. Now replace this in where is it? This equation. So what do we get? E of psi is equals to h bar remains the same, and then we have 2 pi, and k is, what is k? Actually it's k square psi. We can take it as 1. Where did I write the other one? Where did I write it? Where did I forget to write it? No, I did write it, I remember. Yeah, here. This part over here is 1, and that k from here combines with this wave function. Or even if you want, you can write it over there, it will cancel, so it doesn't matter. So then this becomes d square psi over dx square. Remember the negative sign we can end up over here in the starting. It will mean the same thing, and it will become, and then we have psi, and then we have plus f of x. Sorry, what if not f of x? It's actually potential. Sorry, I forgot. So just now I derived Schrödinger equation as known as Schrödinger time independent equation. I came up, this is time independent equation. Oh, I wrote it 2 times, sorry. Then just simply expanding E psi of x, psi with respect to x and t equals to I, sorry, not I, why am I getting ahead of myself? Same thing over here with psi as what we wrote over here. We just expand, or we just derivate this whole thing, but now with respect to, we'll just do it with respect to time. So we get is equals to a e to the power I kx minus omega t. We get d psi by dt as I omega a e psi kx minus omega t. Now we will only look at omega. We will only do first derivation, as this is the only requirement for the time dependent, and then this becomes again what? This becomes omega. I mean psi, and then d psi dx by dt, d psi by dt I omega psi, and then replace this and this. Don't forget this negative sign, which I forgot actually. And then this negative sign, you make this the subject. You know why I'm doing it. dt dt dt, and this becomes I, which can be written as negative I, which can be written as I d psi by dt. Okay, and then finally replacing it over here, h bar omega, we get I h bar and d psi by dt. This is the final version of what we have over here, as this gets replaced by this. So finally we have time dependent Schrödinger equation known as IH bar d psi by dt equals to negative h bar square over 2m d square psi over dx square plus v of x and then psi x by t. Look, as I said in the beginning, every single quantity changed from the normal form to what Schrödinger equation is about, but nothing changed in potential energy. Most of the time it doesn't even gets affected, and it can even equal to zero. How it equals to zero? It's equal to zero for a free particle. A free particle has v of x is equals to 0, so the whole thing becomes I h bar d psi by dt is equals to negative h bar square over 2m d square psi over dx square plus 0, which is not one written. So this is how we get a free particles Schrödinger equation. Now I can derive the equation, or I can even further expand the Schrödinger equation into getting right now over here in this final equation. Very good. This final equation, we have time part of the Schrödinger equation for a system, time part, and the position part as one equation of the system. Okay, but then we can convert this both time, or I can say space time, which sounds more better together, equation, Schrödinger equation, into only space, that's one, only time, and that will be what we will be discussing in the next video. I'm sure it should be what we will do next video. And mostly whenever we talk about solving the Schrödinger equation, it's actually how we can use, leave that, no need to do it. Solving the Schrödinger equation for psi is what gives us the probabilities of the particle having certain properties in that system, where psi can be written as this, it's a real part, and this and the real part, and this is its imaginary part. As if we have imaginary here, that means Psi is actually a complex number or a imaginary number. Or that's how you spell imaginary. Imaginary number. Sorry for the writing. Or I can just wait. Let me forget this. Let me just write I am number. And I think that's it for today.